Lesson 3.5 is about the derivatives of inverse functions. And I'll say right here, we've got a graph of some function f of x, and you might not remember this inverse notation here where there's that -1 up there in the corner. It doesn't mean take something to a power. Please recall that it means that we are taking the inverse of something. Now the steps for taking an inverse, I go over into it a lot more detail in the freestyle, but feel free to check out right here. Example 1, we will go over the steps for finding an inverse. Right now though, we could say that this is the inverse of the graph of f of x. And the question that we're asked right here from these graphs, do you see a relationship between the slope of the graph of f at AB and the slope of the graph of the inverse at BA? And so he's asking, our author is asking, this slope right here and this slope right here, can you tell something about them? And I would say that most people probably can't. I'll give you a hint. We're supposed to be able to see the slopes are reciprocals. And you would want to write that in your notes, because when you're just coming back to this topic, a few months from now, and you want to remember the most important part, boom, the most important part is that the slopes will be reciprocals. And remember that slopes mean derivatives for us. But let's now walk through an actual example where you can see that reciprocal being created, okay? So example 1 says let f of x equal the square root of x. And if I'm going to do that, it says let's sketch that. So I will make a little xy table, x and f of x, and I'll say, hey, what's the square root of 0? It's 0. What's the square root of 1? It's 1. And instead of picking my next point as being 2, why don't I pick 4? Because I actually know what the square root of 4 is. The square root of 4 is a 2. So then I would graph these points. Here's 0, 0. Here's 1, 1. And here is 4, 2. And I know that this is a nice, smooth, parabolic looking curve, like a sideways parabola. That's because I haven't memorized that the inverse of x squared is the square root of x. But right now he says, hey, find that inverse. So I have to prove it to you. Why do I have it memorized? Just because I've done it enough times. How about that inverse then? How do you go about finding it? Well, he mentions up here that there's a reflection across the line, and he even graphs the line right here, y equals x. And so that turns out to be the hint to you. That's always the first step of finding an inverse. So I'm going to say that my original function is y equals the square root of x, just because I want to not have to deal with the function notation anymore. I just want to go back to the old days when things were so simple. I had a y, I had an x. All right, that's because I want to flip those two. So I want to move x to where y was, and I want to move y to where x was. And this is why he says, as a hint, that I need to list a domain restriction. Because the square root of y, remember, we're going to want things to be positive, right? When we had the square root of x before, it is in the domain right here. The domain of this guy, the domain should be such that x is greater than or equal to 0, and we want to keep that domain, okay? We definitely don't want to lose that domain. So how do I go about manipulating this then to see that this is really x squared, y equals x squared? Well, I just square both sides. If I square x, then I get x squared, and if I square the square root of y, then I end up with a y. So, ta-da, I could write y equals x squared like this, but then that doesn't indicate to you that I've found an inverse. So that's where the function notation for inverses comes into play, and I'll actually write it like this. The inverse of this function is x squared with that domain restriction. Okay, so now that I've done all that, just kind of remind you of what inverses are. You might have forgotten, right? We should sketch that graph. We know what the graph of x squared is. For example, an x and an inverse of x function, I could graph 0 and get 0, because 0 squared is 0, 1 squared is 1, and 2 squared, whoops, sorry about that. 2 squared would be 4. So, I'm going to do it in orange, just so it's slightly different, right? So I got 0, 0, I got 1, 1. Those are repeated points. But this next point goes all the way up here, and there is the nice, oops, I like to make sure when I graph that, I like to make sure that I graph it like that. Because remember, in between 0 and 1, the parabola is kind of dragged down by squaring. All right, so now you can see, and by the way, it wouldn't be a bad idea for me to plot 2, 2 and 3, 3. Oops, those are a little bit low, 3, 3 and 4, 4. There's my line y equals x, right? And they do definitely look like a reflection of each other. And he says, let's take the derivative of both f of x and the inverse. And why would we do that? Because we were talking about the slopes being reciprocals, right? So if we find those derivatives, then we'll be able to start looking at those reciprocals. So the derivative of the square root of x, I happen to have it memorized. So the derivative of f of x will be take the power, x to the 1/2 power, bring the 1/2 out in front, and then reduce it by 1. And what I end up with is 1/2 x to the negative 1/2, which again I have memorized as 1 over 2 times the square root of x. And I highly recommend that you get that memorized as well. How about the derivative of the inverse? Here we're going to go ahead and throw out that really cumbersome and annoying notation, and then we're going to make it even weirder because I'm going to throw that prime mark outside of the parentheses. It's supposed to help your eyes track that there is that -1, which means that inverse, and then there's a prime, meaning I'm taking the derivative. And then here I'm going to say what was the input to that original function. It was an x value. And how about it now? Can I take the derivative of x squared? Yes, indeed I can, and I will get a 2x. So the notation is brutal. Not my favorite here. I've never really liked the inverse notation. Not exactly sure where it came from, but it's one thing that I wish we could change about math. So now that I've found those derivatives, let's actually find those specific derivatives at a point, okay? And he says, let's talk about this point 4, 2 and 2, 4, and you might recognize those points as being some points that I graphed naturally just because I already know, what the derivative, or I already know how to take the square root of 4. So if I plug into my original function the derivative at 2, well, I have 1 over 2 times the square root of, at 4. I noticed that right away, didn't I? Because I want to take the square root of 4, and the square root of 4 is 2. So this is going to be 1 over 2 times 2, which is going to be 1 over 4. Yay! And if you're looking ahead, and you've already thought about this, you could see that the inverse, here's my inverse notation. Oh, it's so cumbersome. I'm going to throw in the value of 2, and I will get a reciprocal, right? 2 times 2 is a 4. So instead of having that derivative be 1/4, I flip it, and this is technically 4 over 1 now, which I can just say is 4. So yay, I can see that when I look at the derivative of the inverse, it will be the reciprocal of the derivative of the original, but just not at the same point. Right? I'm not looking when x is 2. I'm starting over here looking at when x is 4, and then my y value is 2, and then I flipped that. Why did I flip that? Well, remember what I did up here? Literally, my very first step is to flip x and y. And if I do so, if I flip that x and y value, then that's how I'm finding an inverse. So when I want to look for that reciprocal slope, how do I go about doing that? Well, I have to flip the point that I'm looking for that reciprocal slope because it won't be in the same place. All right, so what is the conclusion that I can make about these slopes? Indeed, they are reciprocals. And now, I think this is the most important and the most awesome statement in this whole section right here. So if you have a highlighter, break it out. Since the slope is supposed to be the change in y over the change in x, that's what we've been learning is the derivative. It should make sense that if an inverse requires that you swap x and y, well, what would your new slope be? Wouldn't your new slope inverse slope should be delta x over delta y, right? Which is the reciprocal. All right, so now we have a final like statement here. We could say that if I have this point A, B, and it's a point on F, then when I flip A and B and I look on the inverse, then what I get is 1 over the derivative at A. Now, I'm not much for memorizing these kinds of formulas, and so if you can memorize it, great. If you can't, then you just have to remember the steps. So the shortcut is and then find the reciprocal. Okay, now let's see what we get into here as far as more difficult levels of this, because we won't always know what the original function is, okay? And it says, note, when finding derivatives of inverse functions, do not use the same x value for both the function and its inverse. This hardly ever works. It only works if x and y values of the ordered pairs were the same. So if I was looking at that point 1, 1, remember in the graph above, well, then if I flip that 1, 1, then yes, I will find the same slope, but that's only because that already happened to exist on that line, y equals x anyways. So example 2, this is a fantastic example, the weird kind of stuff that you see on the AP exam multiple choice. Let f and g be inverse functions such that f has the function and the derivative values that are shown in this table. Obviously, some of the values in this table will not be useful to me. I'm not intending to use them, okay? It's a little bit of a trick. There's always going to be some extra numbers in there that if you're off on the wrong track, you might accidentally use those numbers, okay? So it says, from the given information, find if each of the following is actually possible. It might not be. The table below is a good way to organize the given information. And this table right here, all of a sudden, when I was looking into these notes, I realized this table is golden. This is the kind of thing that you want to do for sure. With this table, it's all organized the way it's supposed to be, and we're so used to these tables, we think they're useful, but not in this particular case. In this particular case, if I'm looking at -1 and 1, then if I want to find the inverse, what do? Remember that these are supposed to be inverses. F and G, let them be inverse functions. Okay, so then how do I inverse it? Well, I just take this one and I flip it into a -1. And the slope, it said to me that the slope at this point of the original function was 3/2, yes? So what will the reciprocal slope be? It will be 2/3. And where can I locate that slope? I can locate it at the flipped point, 1, -1. Okay, so then what about this next point here, 0, 2? Okay, I can write down 0, 2, and then I could flip that and have a 2, 0. And what is the slope for this guy? It's 2, so what should the slope of that guy be? It should be 1/2. That 2 doesn't look so good. Here, better. Okay, and then how about the last point? I have this 0.15, and then I have a 0.51. And what was the slope? It told me that the slope was 1/2. And so what will the slope be? It will be, over here, it will be 2. And now, from the given information, find each of the following if possible. The table below, we organized our data, and I'm hoping that when we start looking at, question A, B, C, and D, I'll be able to figure out where I'm at, right? So what is G prime of 1? Well, everything that's listed here should technically be G prime. And if I want to know what G prime of 1 is, well, that's when that's where G of 1 lives, and that slope is going to be 2/3. Now, how about G prime of 2? Oh, well, that's where G is 2. And what's my slope? Oh, it's 1/2. Now, G prime of 3, I don't think I can find that because I move from point 1 to 2, and then I skip to 5. I was never given any information about the original function at 3 or the original derivative at 3. So I'm going to say that this one right here is not possible. Not possible. It was just not given information. It's not in my table. All right. D also is not in my table. And I guess E, I'm sorry about there's a little space here. G prime of 5, well, that one I can find because that one was supposed to be 2. I plug in when x is 5 into the G function, and I'll say that the slope there is indicated to me as being 2. So not so bad after all if you use this kind of table. Number 3 doesn't give me a table, right? In fact, it goes back to that, that concept where it just gives me the function. Okay, cool. I know stuff about functions. For example, how about this? Why don't I organize a little bit about what I know into a table? F of x. Hey, they told me that when f of x hits this point 328, I could find the derivative there, right? And then I could plug in 3 for x value and find out what the slope is. So I'm going to do that. F prime of x would equal the derivative of x cubed minus 2x plus 7. See, x cubed, I get a 3x squared. Negative 2x, I get a negative 2. The derivative of a constant is 0, so I'm not going to write that down. And I can evaluate this derivative at my point 3, and I'll have 3 times 3 squared minus 2. 3 squared is 9 times 3 is 27. 27 minus 2 ends up being a 25. So the slope is 25. Yay. The slope at the point where x is equal to 3 of the original function is 25. Now, what do I want to find? I want to find that inverse. And how can I find that inverse? Well, I don't actually have to go and find the inverse of this function. And I leave it to you to pause and even try that for a moment. You're going to find it difficult. This one, I'm not really sure. If I replaced x's with y's, I'm not really sure how I would go about solving for that new position of y. It just isn't possible with the tools that we have now. So that means, what do I do? Oh, well, look, think about it this way. Again, let's call this g of x, and let's do a table just like we did up here. And so I say g of x is got a point, and I'm going to flip that 28 and that 3, 28 and that 3, and then why don't I just flip that, slope from being 25 to 1 over 25, and then ta-da, I've got it. That table was extremely valuable for us, and we have reproduced it again down here, and I can actually now say with absolute certainty that my slope should be 1 over 25. And I didn't actually have to find the inverse of that function. That trick is the trick that you want to use on the AP exam.